Okay, good. So, well, we saw in the last presentation some example of tariffs. In this presentation, I would like to show you how, say, electricity tariff can, say, affect or boost PV development and also impact the grid operation. Okay. So basically, what you see here is, say, a load curve in medium gray, with the PV production in the middle. And we can define self-consumption as the black area divided by the area of the PV production. And if you look at, say, system profitability, say, without any other financial incentive, there is a minimum self-consumption which will provide a profit to the system. And this can be given by this equation, where LCOE is the levelized cost of electricity, PV electricity. Basically, it's given by the total of the cost over the lifetime of the PV system divided by the energy produced over the same lifetime. The exp is the export tariff. So what you get when you export some excess energy produced by your system, and import is just the retail electricity tariff. So basically, we see that system profitability strongly depends on the electricity tariff, so import and export. And of course, you can increase this self-consumption by implementing also batteries. So the question we ask ourselves is how tariffs influence the investment in decentralized PV and storage, how tariffs impact grid operation. Can we define advanced tariffs to help mitigate the impact of large PV penetration on the grid? And is there any strategy or solution to allow a long-term and profitable PV penetration? And I will try to answer those 4 questions in the following slides. So all this work was done on using a case study, which is basically a low voltage grid in the Roman energy grid in Roll, where basically we were considering as data 1 year of loads with a 15 minutes time step, and we're able to calculate for each of the building in this grid the levelized cost of electricity over a period of 25 years. That was the period used as, say, lifetime of the PV system. And we're able to optimize PV and battery operation for a complete year. So for this optimization, basically we optimize both building design and operation. So by building design, I mean the size of the PV system and the size of the battery, taking into account the electricity demand, the irradiance, the cost function for the PV batteries, the tariffs, interest rate, and lifetime of the installation. And using mixed integer linear programming, we're able to calculate the optimized PV and battery capacity, the charging power, PV generation, and curtailment, using as an objective function the total cost, so the OPEX and the CAPEX, taking also into account the interest rate. So what we did in this study was basically we take all this data from this low voltage grid with the load profiles. We designed a couple of tariffs. I will show you the details in a minute. And then using each of these tariffs, optimize the design and operation of each of the building over a 1 year period. And having solved the operation, then look at the power flow calculation of the grid, also to look at the impact of this operation, and then evaluate the result using different metrics. So the tariffs that we used, the first one was, of course, let's say reference flat tariff, reference tariff with an import tariff and export for the excess PV energy. And this tariff was compared to a solar tariff, which was designed to be cheaper at midday when we have sun. A spot market tariff, basically, which mirror the PEX tariff, and this tariff was scaled. Well, basically, all the tariff was scaled to basically give over a 1 year operation the same revenue for the DSO as the reference tariff. We also used the capacity tariff of remote energy, so taking into account the peak of the peak power, and a so-called block rate tariff, where basically for each range of power that is consumed or exported, you have a different electricity tariff. So basically, the higher the consumption, the higher the volumetric tariff, and when you export, the cost decrease as the exported power increase. After doing the optimization for all the buildings and looking at the effect over, say a full year of operation, what we see is that what you see here is the line represents the median of the 41 buildings that we have in this low voltage grid. And so the 5 scenarios or the 5 tariffs that were used. Basically, what we were able to see is that PV hosting is always at the maximum, except for the block rate tariff. Dynamic and capacity tariff promote usually larger battery size. So that's the dynamic effect of dynamic tariff compared to, say, flat tariff. Playing on the spot market, in fact, increase the grid usage. It's basically this effect here, while capacity or block rate tariff tends to decrease the grid usage, because you start to pay for the power. And finally, we see quite a large, say, variance in the payback time between the system. Also, something quite interesting is how tariffs can change the prosumer profiles. Basically, when you have, say, dynamic tariff like the spot market tariff, you see that basically prosumer import or export relatively large amount of electricity. Basically, they play as energy trader, while for capacity for block rate or capacity tariff, of course, you force the operation to minimize the grid usage. We see also quite an important impact on the low duration curve from these different tariffs. The curve that you have here, this red one here, well, not really red, but is the one which is given only by the loads. And we see that dynamic tariffs tend to increase the stress of the grids with quite important import or exporting peaks. While block rate or capacity tariff tends to reduce the stress on the grid. We see also the same for the voltage deviation. Dynamic tariff tend to increase, say, in this case, voltage deviation above or below, while block rate or capacity tariff tends to decrease, say, the voltage deviations. What we were also interested in, say, the long-term evolution. What we did here, I mean, what I just show is basically assume that every system is installed almost over time, overnight. The reality is that system will be installed over a long period, and each installation is going to change the operation of the grid. So what we tried to do was to look at this long-term evolution of PV and battery installation, and also try to introduce constraint in the grid usage to keep the grid in a safe operation. So the methodology we used was first to analyze all the possible system upgrades. So you look at this 41 building and look at PV and battery. And you identify upgrades with a high interest internal return rate of more than 6%. So basically take the most profitable one. You assume that those one will be installed. You calculate the effect on the grid operation. If grid is no more in the safe operation, you reduce the grid usage. So basically you impose a decrease in the maximum possible grid usage. And then you adapt to the tariff to keep a constant revenue for the grid operation. So the DSO revenue for the grid operation. And you do that for every year from 2020 to 2050. What we observed is, you see here's the number of investments. So basically most of the buildings invested over that period of time. And of course, this had the effect of increasing the import tariff and at some point to reduce the grid usage. So basically the import tariff, we show that the import tariff was increased by 30% over that period of time. Starting in 2026, we had to basically impose a grid usage to minimize the impact of the PV condition on the grid. But with that, we're able to reach or to achieve 80% of the possible PV installation over that period of time. And just to give you an idea of what this 80% represent is, if you translate that to the Swiss case, basically it's 30% higher than the 50 terawatt hour objective that we have to somehow decarbonize the Swiss energy system. One of the question is, of course, people investing earlier will see the tariff change. So basically the profitability of the system will change. So what we present here is the real internal return rate over the lifetime of the system divided by minus the one that was computed in the first place when the system was installed. And basically we see that at the end, basically all the system, the profitability remain the same, almost the same for all prosumers. And it's due to the fact that the import tariff with time increase, so the interest also increase, and the grid usage constraint, so the grid usage which decrease will basically force the return rate to decrease, but basically these two effects compensate each other, and we observe a very small variance around an 8% profitability, or it's not 8, it's 6% profitability for the system. So the conclusion, dynamic volumetric tariff promote investment in large storage, but increase the stress on the grid. Capacity-based tariff change battery usage from trading energy to reducing consumption peak. Block tariffs can promote small installation, hence help reducing the stress on the grid. And a long-term installation of distributed PV system can be promoted by tariff adaptation and possibly by operational regulation. Finally, the adaptation of tariffs, in addition to investment cost reductions, ensure profitability for most prosumers. Some outlook to this work would like now to analyze, to do the analysis of the effect of self-consumption communities, to introduce also flexible loads such as heat pumps and EVs, and look at the effect of advanced tariff on this long-term evolution. And also look at, say, having distributed PV and storage could also offer opportunities for the DSO. So basically to manage these distributed resources jointly between prosumer and DSOs. And finally, well, we need to continue working on strategies to minimize the long-term overall investment cost. With that, I would like to thank you for your attention.